Greetings and welcome to the RC Wall Vacuum channel. Today's video is going to be a follow-up on the wireless SCADA system that I've been developing for these fifth scale two-stroke RC engines. And what I'm going to be diving into today is RPM and how to get the signal off the vehicle. What I can tell, there's basically three different ways of doing it. Well, four if you just say that screw it and go out and buy something that some other sucker spent a lot of time developing, but then you don't learn nothing in the process. So we're back to the three primary ways of getting a signal off here that I can think of. Let's take a quick look at some of these. So for the first two types of signal acquisition methods, I got a little Zenoa set up over here and just running a drill motor on it to cycle the piston through its motions. And over here I got the scope set up, and let me get this thing fired up and get some samples off of here. So the first type we're going to look at here is an inductive pickup. And where that would be is it would tie into the ground tab on the primary side of the magneto coil. And that ground tab is the same thing that the kill switch is attached to. So the microcontrollers I'm using require a 0 to 5 volt signal, and it needs to be a nice clean square wave, otherwise it's going to see multiple impulses. Numbers are going to be totally erratic. So I got the scope set the trigger off of one pulse, so let me fire this thing up and see what we get. We try it again, the scope didn't catch it right. There we go. So each one of these divisions is 50 volts, I believe. Yep, we got it set for 50 volts. So you're looking at 200 volt negative pulse that comes off there. So that takes a lot of processing. And then you also see it rings out a lot too. So that signal needs to be processed and cleaned up a lot before I can feed it into a microcontroller. So I am in the midst of trying to clean up and process that signal over here. And the same circuit will apply to the next form of RPM acquisition. And let's take a look at that. So right here is the second form of signal acquisition, and all it is just some wires wrapped around the spark plug wire, and that is considered a capacitive pickup. Since one end is not tied, it's just floating, and it acts as a capacitor. Both ends of the wire would have to be tied down to make the true transformer action for an inductive probe. But let's take a look and see what comes off of that. So I got the other channel of the scope tied into this capacitive pickup. Let's see what we get off of this. Oh, wait a minute, I gotta reset the trigger location. I change the channel it's triggered off of. And that should give us something. Right, let's see what we get off of this. Like I said, this is off the capacitive probe on the spark plug wire. There we go. You can see there's a lot of crap comes off of them. So I got this channel set to 20 volts per division, so let me see what we got here. Yeah, so around 150 volt signal coming off there. And you can adjust that by how many wraps of wire you put around there. But you can see there's a lot of cleanup that needs to be done on that to try to get just a single square wave pulse off of basically essentially that pulse there. Everything else has to be ignored. That's what I'm in the process of doing over here, and I will get more into that in future videos, but for now, for today, I'm going to go on to method number 3. So here's method number 3, and it's a Hall effect switch. If anybody's not familiar with a Hall effect switch, saying Hall effect switch is like saying you drive a car. It opens up, there's a broad range of different types of Hall effect sensors. They all basically respond to a magnetic field in one form or another. It can kind of be grouped into two major classifications. One's going to be a linear analog style, and the other is going to be a digital. The linear analog style are basically meant for reading the intensity of a magnetic field. It can be used for position sensing, and they get used a lot for current sensing because you can take a toroid coil and cut a slot in it and stick the Hall effect sensor up in there and facing into the toroid, and then you can read the magnetic field coming off the coil, and the more current, the more magnetic field, and you can read it that way. But in our application, it's going to be digital. So even in a digital, it's broken up into two more classifications: unipolar, which is what this is, and a bipolar. The bipolar, what happens there is it gets activated when it's exposed to a south pole, and it stays activated until it sees a north pole, which will deactivate it and shut the unit back down. A unipolar will kick on with a south pole magnet, but then as soon as the magnet's pulled away, it shuts itself back off. Now in theory, you could use both in this, I believe, since the magnetos have a north and a south pole on the flywheel, and that's done to set up an AC signal through the coil. Otherwise, without the AC signal, you don't have any transformer action to induct current between the primary and the secondary. And then even once you can break them down even more to, there's different levels of sensitivity. There's ones where the signal faces into it versus swiping it, and it gets pretty crazy. That's what I was saying when you say Hall effect. It's like saying I have a car. It could be any brand. It could be a Lamborghini or it could be a Yugo. I guess as far as the car analogy goes, this could probably be considered maybe a Toyota RAV4. It's kind of utilitarian but reliable. I believe it's this one's made by Melexis. I guess a US 5881 if I remember right. It's in a little TO92 flat package. Let me get the dimensions on it. So it's only 4 millimeter wide by like 1.5 millimeter thick. So what you can see in these Anoas, it'd be no problem at all it can be mounted anywhere along the side here or wherever and easily get the cable back out. But I'm going to be putting into the Taylor 50cc, and that's a little more of a problem. So here I got the Taylor set up, and as you can see, there's not a lot of space to work with in there. And the magnets are up pretty close to the edge here. But getting the cable out of there and getting the chip mounted in there is going to be somewhat of a problem. But hopefully I have a solution. Let's take a look at that. So I 3D printed this little part here that it's going to fit up inside the Taylor. And it's got the matching taper on there, and I got this little slot down through here, and the chip's going to slide down into that slot. And then once I figure out where I'm going to put it this way, I will mill this out a little bit so I have a space to put the wires in there, and then I got to put a little decoupling capacitor on the power supply in there to kind of make sure the Hall effect sees some good clean power coming in there. The bad part is I have to drill holes in this beautiful Taylor engine to mount this thing, which I'm not thrilled about, but sure, that'll avoid the warranty. So before I put the Hall effect into the Kraken, I'm just going to give a quick demo here. I have a different Hall effect attached to a piece of perf board. I'm just going to hold up against this Zenoa that I'm spinning with a drill motor. And we'll capture the signal over here on the scope. And that display is a SCADA display. And the numbers coming out in the EGT and CHT will be bogus because I have nothing hooked to them right now. The RPM numbers will be somewhat valid. I still got to fine tune the software a lot and tie up the loops and stuff like that. But it'll definitely be some decent numbers and to work off of to give a demo. So let's leave it in auto for now. Capture a bunch of them. And we got that. And I'll switch it over to single. And hopefully I'm triggered off of that channel. Yep, there we go. So I guess one thing I got to correct in software when I'm done, when it drops below the speed, it doesn't clear it out. They'll be dealt with in the future. But you can see it's a lot cleaner signal, and it's a rectangle wave, not a square wave, because it's essentially a pulse. And these Hall effects, they go from 5 to 0. That's what I'm counting the pulses off of is that 5 to 0 transition. But you can see it's a lot cleaner in there, and even though like little pulse like that might give the processor a little bit of trouble in the future if I don't give some good conditioning for the signal or the power for it, but worry about that later on. So there's a little Hall effect and decoupling capacitor put together on a little tiny circuit board, and yeah, it wasn't as much of a pain in the ass to put together as it looks like it may have been. Now I just got to go through and mill at the back of that drops in there. So I got the sensor tucked up in there now and the recoil in place. I see I had to cut a little notch to bring the wires out there. So it's partially glued right now. And I'm just going to get it up in there and test it and then finalize setting of the sensor and then pull it out and finish gluing it. But before I pull it back out and glue it all the way, I'm going to give it a quick test run. I just got the sensor hooked to a 5-volt supply and the output's tied to the scope, and I'm just going to run the recoil a couple of times and make sure I get pulses out of it, and then I'll pull it back out. So let's take a look and see if we got some pulses coming out of that. So we got it hooked up, got it energized. I'm sitting 5 volts above ground there. See if we get any pulses off this thing. Oh, there we go. Very good. So I got the part back out of the cracking right now, and that's pre-gluing or pre-epoxy. I got enough glue in it to hold it in place, got it all set, and the next step is to epoxy it in place, and then I'll be putting a servo connector on the end there, 3-pole servo connector. And then I'll probably pull the engine out to install all the way because I can't really see what I'm doing up in there, and I got to make sure the wires are kept clear of the spinning flywheel. So presumably the next video I'm going to be doing on this is going to be packaging both the receiver and the transmitters into more convenient packages and mounting the transmitter on the Kraken and giving it a field test. Got a little work ahead of me on that one, but that will be coming up here fairly soon. So in the meantime, thanks for checking it out.